For over 100 years, the world's best metallurgists studied the iron pillar of Delhi and kept getting the answer wrong. Dry climate theory, secret alloy theory, oil coating theory, hardened surface theory, every one eventually disproven. The correct answer was only found in 2002. Theory 1. Delhi's dry climate protects the iron. Disproven. Delhi receives 650 mm of rain annually. Monsoon humidity exceeds 70%. Theory 2. A secret alloy composition. Disproven. The composition is known, no unique protective element found. Theory 3. Ancient priests supplied oil annually. Disproven. The protective layer is mineral, not a hardened surface. Disproven. The hardened zone does not explain long-term corrosion resistance. In 2002 at IIT Kanpur, a revelation. Phosphorus chemistry explains the corrosion resistance. Ancient India, a modern benchmark for corrosion science. To achieve this in 400 AD required Gupta Empire metallurgists to use a bloom iron smelting process with charcoal reduction techniques refined over generations. Henry Bessemer achieved comparable purity industrially in 1856. The Gupta Empire achieved it empirically 1456 years earlier. Here is what made the IIT Kanpur researchers look in a new direction in 2002. There are many ancient Indian iron objects. Most have rusted. The Delhi iron pillar is exceptional, not just old, but uniquely preserved. If the explanation were simply high iron purity, other high-purity ancient iron objects should show similar preservation. They do not. Something specific to this pillar's forging process created the rust resistance. But what? In 2002, at IIT Kanpur, electron microscopy and X-ray diffraction revealed the pillar's secret, a protective layer of iron-hydrogen phosphate hydrate. What they found was a compound that nobody had specifically looked for before, iron-hydrogen phosphate hydrate, a crystalline mineral layer 1 millimeter thick. The answer? IIT Kanpur 2002. Iron-hydrogen phosphate hydrate from phosphorus-rich Gupta iron, introduced through the specific charcoal used in the bloom furnace. The 2002 IIT Kanpur analysis revealed iron-hydrogen phosphate hydrate from phosphorus-rich Gupta iron. Reacting with moisture, it formed a self-sealing crystalline shield, protecting the iron ever since. When phosphorus-rich iron is forged at high temperatures and then exposed to humid atmosphere, iron-hydrogen phosphate hydrate forms at the surface as the iron cools. Then the irony of modern production removing the key ingredient. It is a one-time formation process, requiring the specific combination of phosphorus content, forging temperature, and cooling conditions that the Gupta process naturally produced. Then the irony of modern production removing the key ingredient. This phosphorus-rich charcoal, combined with high heat and humid cooling, created a one-time self-sealing layer. Modern iron production removes phosphorus, making this ancient protection impossible to replicate accidentally. The 2002 IIT Kanpur study launched a new field, ancient Indian metallurgy.
Now, ancient India is the benchmark for passive protective film formation in corrosion science.
What emerged was a picture of iron production sophistication, particularly in phosphorus management, that was far more advanced than previously recognized. Today, material scientists reference the Delhi iron pillar as a benchmark for corrosion resistance, a standard ancient India set that took modern science 1600 years to document. The iron pillar of Delhi was not a mystery because ancient India was primitive. It was a mystery because modern science spent 100 years looking in the wrong places. When IIT Kanpur looked in the right place in 2002, the answer was there, exactly as the Gupta Empire metallurgists had left it 1600 years earlier. Follow Stone&Cipher. Every week, the ancient knowledge that took modern science a century to catch up to.